Hey pre-calculus friends, here we are in section 8.2. We're going to be talking about algebraic vectors. Our notes and vocabulary today start off by giving us a way to kind of represent a vector as an ordered pair. And so I think an example would be helpful to understand what this section is saying. So let's look at an example. So suppose we have this vector here that I have highlighted in pink, and the vector has a beginning point and an end point. And so that's what P1 and P2 refer to. So let this be the initial point. This is our P1 and this is our P2, being the terminal point. The ordered pair for this vector, so let's call this, I can call it P1, P2 vector. I'm going to call it vector A, just so we can kind of think about it as a singular thing, but this is totally fine way of writing it as a vector. The ordered pair that represents this vector will be the difference between the x's and the difference between the y's. But when we find that difference, we need to make sure that the terminal value, so for me it's 4, 8, the terminal x term is what I'm subtracting the initial x term from, and the terminal y term is what I'm subtracting the initial y term from. So the way I would write this is I would use an ordered pair, but I'm going to actually, instead of using parentheses, I'm going to use what looks like greater than less than signs, kind of like I don't know, an arrow-like parentheses. I don't know if it has a name, but so this would be the ordered pair that I'd use to refer to this would be 3, 4. Does that kind of make sense? And if you think about it, if you think about the displacement is 3 units in one direction and 4 units in the next direction. Let me see if I have that right. Is it 3, 4? 4 minus 1, 8 minus 4, 3, 4. So the displacement of the point would be 3 units this way and 4 units this way, even though it doesn't look like it. My graph isn't drawn to scale. Does that make sense? So this ordered pair is what I'd use to refer to this vector. And of course, the magnitude, which we know is the length of the vector, we can get from, and that's what this is here, the distance formula. So we remember the distance formula, the distance between those 2 points, or I should write it the way we're dealing with it here, the magnitude of A, I'll try to be neater, the magnitude of A is going to be just the distance of that, or the length of that segment, and we know what that is. That's going to be the difference between the x values squared, so that's going to be 3 squared, 4 minus 1 squared, 8 minus 4 squared, which is going to be 16, or 4 squared 16, and we know 9 squared plus 16 is going to be the square root of 25. We would get 5 as the length or the magnitude of this vector. Okay, so that's what we kind of get the power to do, and being able to translate vectors into this ordered pair gives us the power to do some cool vector operations. So let's say vector A was was referenced by this ordered pair a sub 1, a sub 2, and vector B was referenced by b sub 1, b sub 2. Then there's some real number k. Here are the things that we get to do. We can do addition. If we are adding vectors, we can add the same parts of the components of their ordered pair. So a sub 1 plus b sub 1, comma a sub 2 plus b sub 2 would be the new vector, the addition, the sum of these two vectors together. Subtraction, similarly so, we will be subtracting the quote unquote, I'm going to call it the x component, you know what I mean, but the x-like components of these two vectors, and then the y-like components. And look at the order. Notice that if A is first, we're adding, well, addition's a little bit different because it's, we've got the commutative property, but not so with subtraction. So we got to be careful. If it's if it's vector A minus vector B, you want to make sure that you're doing A minus B in each of those, a sub 1 minus b sub 1, a sub 2 minus b sub 2. And then scalar multiplication is pretty cool. If you're multiplying vector A by a scalar k, you're going to multiply each component of that vector by k, each of those parts. I keep calling it components because you might realize, remember when we talked about components in the last section, we talked about the idea that going this way is like a horizontal component, and then going this way, let me use a different color, is the vertical component. And if you notice, that's what we end up with when we talk about the vector. We end up with the ordered pair that refers to the vector. So the ordered pair is, I know this orange doesn't look like 3, but it's 3, and this green doesn't look like 4, but it's 3, 4. Make sense? So that's really the component parts of the vector. Okay, let's look at a couple other things. One more vocabulary term we need to look at is the unit vector. The unit vector is considered a vector with a length of 1, with a magnitude of 1. So the unit vector, as we have it here, can be aligned with the x-axis or the y-axis. When we talk about the unit vector in reference to the x-axis, a horizontal unit vector, we refer to that as I vector. And when we have a vertical vector, the unit vector, that's J. And this is how you would write it down. It kind of makes sense. If you think about I in reference to its beginning point and end point here, and we think about the difference between the x values and the difference between the y values, you'll see the y values are the same, so we get 0, and the x values are, the difference between them would be 1 step. So this 1, 0 makes sense as the ordered pair we're going to use to refer to the I vector. And the j vector, similarly, we can talk about the initial point and the terminal point, and the difference between the x values being 0 and the difference between the y values being 1. Okay, with that, let's get to some practice. Here in example 1, we're going to write the ordered pair that represents the vector from point x, which is at -3, +5, let's say somewhere here, and point y, which is at +4, let's say here, and -2. All right, so we've got these 2 points. I'm going to write them down so we can keep in mind what their values are. And now what we want to do with this information is we want to find the magnitude and the ordered pair. So that represents this. So you remember from our rule, we know that we need to consider what the direction is. Since the vector goes from x to y, in that way, we're going to consider y.2 and x.1, and we remember to figure out what this vector is in terms of the ordered pair writing that we just learned about. We're going to subtract the second term, the y value, the x value of the second term. No, we're going to subtract the first term from the second term, right? You know what I mean? The terminal, from the terminal term, we're going to subtract the other one. All right, you know what I'm talking about. So the displacement basically for in the x direction from -3 to +4 is 7. That's ultimately what we're figuring out here. So 4 minus that, and then from -2 minus 5, this displacement is going to be kind of like in the negative direction, because in this way, notice that our vector is kind of going in the positive x value but negative y. So it makes sense that when we do -2 minus 5, we get a -7. Y'all with me? I hope so. I hope that made sense. So that's the first part. We wrote it as an ordered pair. Then we've got to find the magnitude. What I like about the magnitude is that the magnitude, since we've already found the difference between the x's and the y's, we know that the magnitude is going to just be the distance formula, which requires us to find the distance between the x and y, and then square those, add them up, then take the square root. So we know that this would be 4 minus a -3, 7 quantity squared, and then -2 minus 5 plus -7 quantity squared, and the square root, that's our distance. And then so now we get 49, and 49 is 98. We get the square root of 98, which we recognize is going to be pretty close to 100. 9.8 or 9.9 is going to be pretty close to 10. 9.8 or 9.9 might be a good approximation. If we wanted the exact answer, however, we would reckon the fact that 49 times 2 gives me that 98, and then I can write this as 7 square root of 2 if we wanted the exact value. But if we wanted to approximate it, I should probably grab a calculator to confirm, but it's going to be something like 9.8 or even 9.9, really, really close to 10. Square root of 100 is 10, and square root of 98 has to be very close to that. And so example 2, we're going to start demonstrating the second set of principles where we looked at the algebraic things that we can do, add, subtract, actually arithmetic, add, subtract, and multiply by a scalar. So here we're given some values for different vectors, the different ordered pairs that represent these different vectors. And you guys get this. You know what you're going to do. We've done these types of things very many times. So since we are adding vector m plus vector p, we're going to add the ordered pairs that make that up, and we'll do it in exactly the order that we have here. So 5 plus a -4, -1 rather, 5 plus -1, I'm thinking the answer is 4, and so I said -4. -7 plus 3, that's going to give me a -4, and this is the value that we need. So we found that. I was making sure they didn't want us to find the magnitude, but not so much. So mn, order is important, so m minus n, we're going to subtract 5 minus 0 and get 5, and then we'll do -7 minus 4, and we get -11. Here we're multiplying this scalar 7 times vector p, and so we just multiply each of the terms. So we get -7 and a positive 21. Finally, we've got a couple of things to do here, but not too hard for us. We can handle it. So we're going to multiply 2 times this vector, and so we get, instead of writing the 2, I'm just going to do it. We get 10 and -14. That's 2 times the vector m plus 3 times the vector n, which is going to be 0. 3 times 0 is 0, and then 3 times 4 is 12. And then we're going to subtract from that vector p, and just for kicks and giggles, I'm going to write vector p down. And I am going to do this from left to right as we are used to. So we end up with 10, -2, and when I subtract from that this vector that's represented here by -1, 3, I end up with 11, because negative, and then I end up with a -5. All right, so a little bit of work, but not too much. Nothing that I know you all can't handle. So example 3 is going to refer to this situation. We've got paramedics Paquita Gonzalez and Trevor Howard are moving a person on a stretcher. Ms. Gonzalez is pushing the stretcher with a force of 135 newtons at 58 degrees with the horizontal, while Mr. Howard is pulling the stretcher with a force of 214 newtons at a 43-degree angle with the horizontal. What is the magnitude of the force exerted on the stretcher? So this sounds like addition of 2 vectors, okay? And these vectors are represented by these 2 individual situations. So let's draw it out so we can kind of think it through. Okay, for simplicity's sake, let's see if we can kind of recreate a dynamic where we're thinking about these. So I'm going to call one the G vector, which is Ms. Gonzalez, and we know that she is pushing this with a force of 135 newtons at 58 degrees from the horizontal. So let's say this is our 58 degrees here, and let's represent this vector in this way where we know that the force is 135 newtons. And then similarly we'll do the same thing with Howard, where the force of his vector is 214 and the angle is 43 degrees. And so what we're going to do here is, remember how we were taking basically the horizontal and vertical components to create the ordered pair that is equivalent to the vectors that we were dealing with. We're going to do the same thing here. We're going to have to use some trig though, because when we think about those component parts, we're going right back to right triangle trig, where we need to think about if this were a triangle and we know that the force is 135 along this angle, along this passage, we can figure out what the vertical force and the horizontal forces are. All right, so we'll do that for both of these. Let me go ahead and write that in. And this way, what we'll do is we'll ultimately figure out kind of like what this ordered pair is, and figure out that what this ordered pair is would be the exact value that we would use to refer to the vector, as the other ordered pair, the beginning place that we have it is the origin, and if we subtracted the x terms and the y terms, we get just this point. Y'all with me? I hope so. We can talk about it later if it's really kind of confusing. Okay, so we know that's Newton. So now how do we find this measure here? We would find this measure here by using sine, or the inverse sine, or no, actually not the inverse sine. We would use sine to find this value here, the y value, and we would use cosine to find x. So let me write it in here for us to see. So the sine of 58 degrees is equal to opposite, that's what we're looking for, that y value, over hypotenuse, which is 135. And therefore, with a calculator, all we need to do to find y is to basically say that y, this term here, is going to be equal to 135 times the sine of 58 degrees. I know I'm writing kind of tiny. I want to keep this organized so that the work we do makes sense. So the value I'm going to get here is 135 times the sine of 58 degrees. Similarly, I know that the cosine of this angle 58 degrees is going to be adjacent. Cosine of 58 is going to be adjacent over hypotenuse, or x over the 135, and therefore to find this value here, I'm going to have to take 135, multiply 135 by cosine of 58 degrees, and I'm going to get that x value. So I'm going to go and do that now, and then I'm going to plot the answers down, and we'll do the same thing for Howard's vector as well. So with the calculator's help, we see that we get approximately, for the horizontal component, 71.5, and the vertical component 114.5. And now we'll do the same thing for Howard's vector. So we'll see that using the hypotenuse here, or the actual force Newton value, we can find the x component of the force by taking 214 times the cosine of 48 degrees. And then the y component of the force can be found by taking 214 and multiplying it by the sine of 43. Why do I have 43 and 48? Because they both should be 43. Thank you, guys. I know you're telepathically telling me even before I set the video that I'm doing it wrong. Sorry. So there, we do 214 times the cosine of 43, 214 times the sine of 43, and from there we're going to get that the two components are 156.5 and 145.9. So now that we have these two vectors, vector G written in 71.5 as 71.5 comma 114.5, and vector H written as you see here. Now that we have it in this form, we can add these two vectors together. When we add the two vectors together, we get the sum of the vectors, and now we get basically the total force, and from that value we can then find the magnitude. And so when we add those together, we get the following. And then now if we want to find the magnitude, we know that this is kind of like what would be happening if we were at the origin. So we don't have to do the difference. We just have to take the square of each of these components, add up the squares of the components, and then take the square root of that in order for us to find that's not a 6, in order for us to find the magnitude of this vector, which we're going to write, I guess, like that, with the absolute value there. So we get that the net force on the stretcher in this situation is about 346 newtons. All right, hopefully that made sense, guys. Let's go ahead and look at our last example. Finally, this last example has us writing this vector AB when it starts at 4 negative 1 and goes to 6, 2. We're going to write it as a sum of unit vectors. And you remember, when we talk about unit vectors, we're talking about vectors with a magnitude of 1, and specifically the unit vectors that we'll talk about will be the unit vector I and the unit vector J, which we recognize as one. I is going to be a horizontal, 1 unit horizontal, whereas J is going to be 1 unit in the vertical direction. All right, so if we keep that in mind and we think about what's happening here, the first thing that might be helpful would be for us to write AB as as an ordered pair, and we remember how we do that. B being the terminal, we would do 6 minus 4, which gives us 2, and 2 minus a minus 1, which gives us 3. So this is the ordered pair that refers to our situation where 2 is the horizontal displacement and 3 is the vertical displacement. So what that means is I can write this as 2i, right, plus 3j. And that's really it for us. If you have any questions with this, please let me know. I know this is kind of easy, but it takes a little thought, takes a little time to kind of think it through and make sure it makes sense. If you might even kind of fool around with some Pythagorean theorem just to see how things are moving when you create different vectors to add up, if you want to check out how they actually align, and you'll see that what we have here is working out fine. Listen, take it easy, guys. I look forward to talking to you soon. Bye-bye.